to the latest episode of Thermodynamics. Today we're going to talk about thermal expansion. Let's first watch an experiment. So here we have a copper ball that is being heated, and originally the copper ball is able to fit through the ring. Now, as the copper ball is being heated, you'll see something that's really interesting. So right now the copper ball is still being able to pass through the ring. As it's continually being heated, the ball's temperature continues to increase. Then the ball starts getting stuck into the ring. Why does that happen? Well, both the ball and the ring are made of copper, specifically tiny atoms or really small chunks of copper. These copper atoms are not fixed to their places. They vibrate around and constantly just bump into each other, even though when it's very cold or very hot. The atoms will keep bumping into each other no matter what. Well, the hotter the temperature, the quicker the atoms will move around, since then the atoms are more excited and will have more heat energy. The copper ball we saw was very hot since it had already been sitting in the flame for 3 minutes. Thus, the atoms were moving out really quickly, and they were getting pushed apart by the constant collisions, which makes the ball expand. Well, by how much do certain materials expand? Firstly, gases expand more than liquids, which will also expand more than solids, because molecules between solids are more strongly attracted towards each other than liquids and gases. The table shows how much volume and length an object will gain for every temperature increase of 1 degree Celsius. Think about it. Why does the rate of volume change equal to around 3 times the length of change in solids? For example, aluminum expands by a factor of 25 per million per degree Celsius, while the volume expansion coefficient for aluminum is 75 per million per degree Celsius. Well, we call the coefficient of linear expansion, or how much length it gains, alpha. And we call the coefficient of volume expansion beta. Obviously, the material's length will expand in every single dimension. So, for example, a cube of aluminum that originally had length 1 will now have a length of 1 plus alpha, and now a volume of 1 plus alpha cubed. And if we do a little algebra and expand this expression, we'll get an expression of 1 plus 3 alpha squared plus alpha cubed. Now, 3 alpha squared and alpha cubed are really small, because alpha is really small already, so we can just disregard this. And so beta is very close to 1 plus 3 alpha, and that is why the volume expansion coefficient is actually 3 times the linear expansion coefficient. Now let's talk about how thermal expansion can be used in our world. On the left, we have an internal combustion engine, the type of thing that powers gas cars. So, an internal combustion engine rapidly heats up the air inside what it calls a cylinder, and the air actually pushes the piston. Since the air is rapidly heated up, it also pushes the piston down while it expands, which powers our cars. In the middle, we have a couple thermometers. Now, the reading we obtain by the thermometers is just the level of the red liquid. And so, the higher the red liquid rises, the higher the temperature it is. Thermal expansion controls how much the red liquid expands, and thus makes sure that our thermometers are accurate. Lastly, we have a close-up of a train rail on our right. We notice that there is a gap between 2 parts of the rail, and that is because the rails will expand in the summer compared to the winter. And thus, if they expand and they touch in the summer, they might compress into each other and make the iron warped. We don't want that, so we want to give the rails plenty of wiggle room so that they don't expand into each other and instead expand into the gap. After watching the ball and ring experiment, we discovered what thermal expansion was. We also found out why it happened. In short, atoms keep bumping into each other, and the hotter it is, the quicker the atoms move, and the more space they will need to move around. We also know how much they expand by. For example, the volume actually expands about 3 times as quickly as the length, and gases expand more than liquids, and liquids expand more than solids. We also know that thermal expansion relates to our daily lives. For example, they are taken into account when designing railroads. We rely on it to measure temperature in thermometers, and it's also essential to the functioning of our cars. Thank you, and I'll see you next time.